show us, besides fuses, because I was looking for a fuse, what an ellipse is. An ellipse is basically a set of points that when you add them together, they always stay constant. As you move this around.
That's cool.
So, what happens here is that the curved loop, a curved line forming a closed loop where the sum of the distances from 2 points, the foci, to every point in the line is consistent. It's basically an ellipse. It's a squished circle.
Squish.
It's two parabolas meeting in the middle. Think of it this way, it's a parabola going in both directions. Ellipses can be stretched across the x-axis, or they can be stretched through the y-axis. It's very easy to tell what they do. So let me go back. So I'm sorry that website wasn't as cool as the other one. So here's what's going on. Within an ellipse, you don't need to write all of this out here, is that, you wind up with these two generic ideas. You have what are called major axis and a minor axis. A major axis for an ellipse is the one that's stretched longer than the other. So if I'm looking at the ellipse on the left, this means that the horizontal axis would be the major axis because it's stretched further this way than it is vertically. The vertical axis would be considered the minor axis. Whereas the one on the right, it's opposite. The vertical axis is stretched longer than the horizontal axis. And what happens here is that you have within the ellipses, that's the plural of ellipse, you have vertices, vertex, and you have what are called co-vertices. The vertex are always on the major axis, whether it's stretched left and right or stretched up and down. The co-vertex then is on the other axis. And you get these two generic forms of the equation. What happens then is that within those generic forms of the equation, something that's very easy to notice. So we have x squared over a squared plus y squared over b squared is 1, or x squared over b squared is y squared over a squared is 1. What's the difference? The a's and b's switch. What happens here is that this value of the a value is always going to be the larger of the two numbers. So if the larger value of the two denominators is underneath the x, it's stretched left and right. If the larger value is underneath the underneath the y value, it's stretched up and down. That's how you're able to tell whether or not it is left and right or up and down for a major axis. Okay? Again, what happens is the a value, if the a value will always be the bigger of the two numbers, the a squared value. So if the a squared value is underneath the x, if the bigger of the two denominators is underneath the x, it's stretched left and right. If the bigger of the two numbers is underneath the y, it's stretched up and down. Couple of actual real examples of this, and you'll go over this real fast. Okay. Again, just like we did with parabolas, the parabola always was opening towards a focus. You see that as well within the ellipses. The ellipse, if you think about it, in this case, that's just half of a parabola with the vertex here and the focus looking at it. It's kind of the same idea. Here's your vertex at A. The focus is still the value of C. And I'll show you guys how to find all these values here. Really quite simple. So again, everything is centered at the origin for right now. So we're going to be working on the XY grid itself. Your ordered pairs are going to be very easy to work with. Your vertex for when it's stretched left and right is always going to be at A, 0, and negative A, 0. Your co-vertex is always going to be at 0 and B, and 0 and negative B. And I'll show you how to find C here in a second. Whereas it's Opposite then when you're looking at when it's stretched vertically. When it's stretched vertically, again, your vertex then, if it's stretched vertically, your vertex is going to be now at 0, comma A, because it's underneath the Y, and the opposite of A, and the co-vertex at B0 and negative B0. All right. When we're plotting these points, what we're going to find here, given the equation, is that you're going to know your A and your B right away. There's really only one thing you have to find, and that's C. And I'll show you that here now. The focus of the ellipse, the C value, is always found by A squared minus B squared is C squared. And that's where your focus is going to be. So the focus, depending upon which one you're working with, if your focus for your stretched left and right, since we're at the origin, it's going to be at C, comma 0, and opposite of C, comma 0. Whereas on the other one, it would be at 0, comma C, and 0, comma negative C. Does that make sense? Because it's stretched up and down, so the focus is looking, it's on that same y-axis. It's going to have the same value for x as A, or it'll have the same value for y as A. Like I said, this looks a lot weirder than it really is. Let me show you an example. Nine x squared plus 16y squared equals 144. And I need to graph this. The standard form of an ellipse always equals 1. How do I make that equal 1? Correct. Divide everything by 144. The standard form of an ellipse is always going to equal 1. So in order to make this work, you just divide everything by 144. And you wind up with, what's that? X squared over, isn't that 16? I think you get that, right? So now you're in standard form. Which one of those is bigger, 16 or 9? 16. So is the 16 underneath the x squared or the y squared? It's underneath the x squared. So is this going to be stretched left and right or stretched up and down? Left and right. So by doing that, I know now that my a squared is 16, b squared is 9, c squared is going to equal 16 minus 9. So what is c squared going to equal? What? Remember, I'm just taking a squared and b squared. A squared is 16, b squared is 9. So 16 minus 9 is 7. All right? So that means that my value of a is going to be at plus or, let me do this, a is going to equal plus or minus 4. B is going to equal plus or minus 3. And C is going to equal plus or minus root 7. Again, very, very straightforward. We find out what, we are able to figure out what a squared is, what b squared is, and what c squared is. We can take these square roots really fast. More often than not, you're going to have square roots that work for your vertices. The foci usually comes in a little bit weird, but it's just a root usually. You'll use decimal equivalencies when you print these out, plot these out. Okay. Again, you guys told me that this is going to be stretched left and right because the a squared term is larger here, so I'm going to make a little over-exaggerated knowing that I'm going to go left and right with it. And you know everything else to do here. What we wind up doing is, well, take a XY grid. If I know it's being stretched left and right, I know that my vertex for this is going to be at the values of a, comma 0, plus or minus. So vertex are at 4 and negative 4. My co-vertexes are where? Vertices, excuse me. Positive and negative 3. Make my oval. Funny, my ovals look like my circles. Wish I could throw something. And then lastly, what's the decimal equivalent of the square root of 7? It's more than 2, less than 3, 2, 6 maybe? 2.6-ish? Yeah. So about here, and about here. So what we've been able to do then is we now know that our vertex are at 4, 0, negative 4, 0. The co-vertex, you look if I use CV for that, is at 0, 3, 0, negative 3. And then the focus is at root 7, 0, and negative root 7, 0. And that's it.
There's no shifting?
Not yet. We will shift these. We will shift these. But again, you'll notice the shift version of this is just going to be x minus h quantity squared over a squared plus y minus k quantity squared over b squared. And again, it's going to have two different versions of that because a squared is always the larger of the two, and it tells you the direction of which one's being stretched. Scary? One thing to remember is that get the value of c, take a squared minus b squared. Okay? When we get to the hyperbolus next week, it's a little bit different. So let's just do one more of these, and then we'll call it a day. Try that one on your own. Did we get all that info okay? Is this one stretched left or right or up and down? Left, right, very good. Again, like we did before, just do a quick little representation so you know which way you're going. Just it kind of helps out a lot. And then it's just a matter of plotting it. Remember, everything's centered at the origin, so you have to worry about any shifts. There's nothing too crazy. 2, 3, 4, 5. 2, 3, 4, 5. Over to C at 2. Well, if you think about the square root of 21, it's less than the square root of 25, but it's greater than the square root of 16. So it's going to be closer to the 5, so we're guessing 4.7?
4.5, 6.
So 4, 6. So about here, and about here. So now I just list them out. Well, vertex, 5, 0, negative 5, and 0. I know some of you guys probably want to go plus minus 5, comma 0. Don't do that because when you shift these things, it's not going to be that clean. Your co-vertex, 0, 2, 0, negative 2, and focus at root 21, 0, negative root 21, 0. Okay. Not so bad?
No, it's good.
All right. Let me give you guys a couple of these to try. Let's get back here. Let's see. It's on 613. I'll give you a whole whopping 6. I know.
Gee,
It's a lot. I know. So this is 10-4. Page 613. 30. Oh, I'm sorry. That's 4. I'm sorry. It's 7.
Are you kidding? We only have a 5.5-day weekend.
I know, you'll have to pace yourself. These These four are graphing. Same idea like we just did with those two examples. List everything out. These last three, you're given a vertex and you're given a co-vertex. Write the equation.
That's just supposed to be a challenge. Like,
It is a challenge because I didn't show you how to do it.
if we don't know how to do it, it's not that middle of.
Well, you should be able to figure it out. You guys are
tricky.
somewhere. No, it's tricky to rock a rhyme, but it's not tricky to do this.
What about if we something
Let's see what she did.
Thank you. I got a fist stomp of my bad humor.